The topic of this DVD tutorial is Arc Flash calculations and labeling requirements. Take a moment to review the disclaimer now displayed. While the methods discussed in this tutorial are the best means we have today to estimate arc flash hazards, they do not address all of the variables or risks associated with arcing faults. Engineering judgment is required for arc flash calculations, and the information presented in this tutorial should not be interpreted as a recommendation to work on or near energized conductors. Working on or near energized electrical conductors is never recommended and should only be done when it isn't possible to de-energize the circuit. This tutorial will review the arc flash labeling requirements in NEC Article 110.16, arc flash calculation requirements in NFPA 70E, and expanded calculation methodology and procedures in the IEEE 1584 standard. We will also discuss some examples and explore important concepts and issues. NEC Article 110.16 requires arc flash warning labels. The article states, switchboards, panel boards, industrial control panels, and motor control centers in other than dwelling occupancies that are likely to require examination, adjustment, servicing, or maintenance while energized shall be field marked to warn qualified persons of potential electric arc flash hazards. The marking shall be located so as to be clearly visible to qualified persons before examination, adjustment, servicing, or maintenance of the equipment. This picture demonstrates minimum labeling requirements based on the 2002 NEC. The label states only that a potential flash hazard exists. For improved safety and worker compliance, it is recommended to provide additional information on the label, including the flash hazard boundary, working distance, and required personal protective equipment, PPE. While it's obvious that insufficient PPE is dangerous, overclothing workers may also increase the risk of an arcing fault due to limited mobility and visibility. NFPA 70E is the standard for electrical safety requirements for employee workplaces. Originally requested by OSHA, the National Fire Protection Association developed 70E as a standard for electrical safety. This document provides requirements for electrical safe work practices, electrical shock and arc flash boundaries, and proper personal protective equipment. This standard addresses safe work practices for both qualified and unqualified workers. IEEE 1584 is a standard released in 2002 and revised in 2004. It provides empirical equations to estimate arcing fault current, incident energy, and flash boundary distances for work in 208 to 15,000 volt three-phase electrical systems. When approaching electrical equipment, most people think of shock hazard, but many don't recognize the danger of arc flash hazards. To understand the arc flash hazard, it's important to understand the difference between an arcing short circuit and a bolted short circuit. When a bolted short circuit occurs, the circuit path bypasses the load and shorts the circuit. The current that flows can be hundreds or thousands of times the normal load current. The energy flows through the circuit and is not released into the environment. However, there are serious hazards associated with bolted short circuit currents, such as protecting components from rupturing and ensuring overcurrent protective devices have adequate interrupting ratings. In contrast, an arcing fault is the flow of current through the air between phase conductors or between phase conductors and neutral or ground. Arcing faults can have current magnitudes that approach the bolted short circuit currents, and arcing faults release energy into the environment. The magnitude and duration of an arcing fault is dependent upon many variables and is therefore difficult to predict. When an arcing fault occurs, the result can be extremely high temperatures, a tremendous pressure blast, intense light, sound waves, metallic vapor, and shrapnel hurling at high velocity. An accidental slip of a tool or a loose part tumbling across live parts can initiate an arcing fault in the equipment. If a person is in the proximity of an arcing fault, the flash can cause serious injury or death. The point of the NEC 110.16 warning label is to remind qualified workers of the arc flash hazard when working on electrical equipment. A phase-to-ground or phase-to-phase arcing fault can quickly escalate into a three-phase arcing fault due to the ionized gases that form around the phase conductors. While all of these hazards exist, This tutorial is focused specifically on protecting workers from incurable burns caused by the extreme heat. Let's look at an actual arc flash incident. In this example, an arcing fault occurs in a distribution substation. The protection doesn't clear the fault for several seconds, resulting in catastrophic damage. Fortunately, no one was present within the substation flash boundary area when the arcing fault occurred. The substation example highlights one of the most important considerations of arcing fault calculations, that is, how long it takes the upstream protection device to clear an arcing fault. Since the arcing fault current is less than the bolted fault current, typically between 38% and 89% of the bolted fault, it may take substantially longer to clear an arcing fault. It is prudent to think of an arcing fault current as a possible range of current using assumptions that produce a minimum and a maximum arcing fault current. This slide depicts a fuse melting curve and a tolerance of arcing fault currents. At the maximum arcing fault current, the fuse will melt before 0.01 seconds and may operate in the current limiting range. However, at the minimum arcing fault current, the fuse will take about 100 seconds to clear the fault. The amount of energy released is a combination of the current and the time. As seen in the substation example, the long trip time was catastrophic. The point here is that a smaller current may be worse than a larger current since the trip time may be substantially longer. Let's look at an example of an arc flash incident filmed in a lab. In this case, the system is 480 volts, the available fault current is 22,600 amps, and the protective device clears the arcing fault in 6 cycles. Each slide represents approximately 1 cycle. During the first cycle, the arc releases significant energy, including light and heat. At 2 cycles, vapor and debris can be seen. At 3 cycles, the pressure and sound waves begin to move the worker. At 4 cycles, the equipment and worker are engulfed in flame. At 5 cycles, smoke rises from the fire. At 6 cycles, the fault is cleared, but the damage is already done. A picture taken after an actual arc flash incident shows the substantial equipment damage and the outline of the 2 workers subjected to the flash energy. Another graphic example of an arc flash incident demonstrates that clothed areas can be burned more severely than exposed skin if improper clothing is worn. This is because the clothing can ignite and continue to burn after the arcing fault is cleared. Faster operating times and current limiting devices can reduce arc flash exposure. The following example uses the same conditions as the previous lab example, 480 volts and 22,600 amps of fault current. However, this time a current limiting device is used that clears the arcing fault in less than 1/2 cycle. Note that the faster operating time only occurs in the current limiting range of the protective device, and the minimum arcing fault current may be below the current limiting range in many cases. Again, each slide represents approximately 1 cycle. During the first half cycle, some light and energy is released, but the fault has already been cleared. At 2 cycles, the environment begins to return to normal. 3 cycles, 4 cycles, 5 cycles. For this case, by clearing the fault in less than 1/2 cycle, there is no perceivable damage. Possible costs associated with not performing arc flash calculations can be high and include non-compliance fines, lost productivity, increased repair costs, medical expenses, legal costs, and most importantly, loss of life. The arc flash calculations and labeling requirements are intended to help reduce injuries and death. While not a requirement in the National Electrical Code, it is important to review some regulations in OSHA and NFPA 70E related to working on live equipment. OSHA regulations state that workers should not work on live equipment except for one of 2 reasons. 1. De-energizing introduces additional or increased hazards, such as cutting ventilation to a hazardous location. Or 2. It is infeasible due to equipment design or operational limitations, such as when voltage testing is required for diagnostics. Note that NFPA 70E states essentially the same requirement and adds, when it is necessary to work on equipment live, you must follow safe work practices, which include assessing the risks, wearing adequate PPE, and using the proper tools. Note that even when de-energizing the system, performing a voltage test requires proper PPE. The arc flash hazard must be assessed prior to working on equipment, and NFPA 70E stipulates 3 shock boundaries and a flash protection boundary that must be known and observed. The shock boundaries are dependent on the system voltage and can be found in NFPA 70E. NFPA 70E also provides methods to determine the flash protection boundary. It is possible to calculate the flash protection boundary and incident energy exposure level when the available voltage short circuit current, the minimum sustainable arcing fault current, and the trip time of the protected devices are known. NFPA 70E provides the formulas for this critical information, as well as other important information on safe work practices, required PPE, and tools to use. A qualified worker should not enter the flash protection boundary without wearing proper PPE. As the video showed, electric arcs release a lot of energy, which takes on many different forms and may be destructive. One form of arc energy is incident energy, which is the radiant and convective energy per unit area. Incident energy causes burns, which is a major life safety hazard. As a benchmark, 1.2 calories per square centimeter is the energy at which a second-degree burn will occur. At 3 calories per square centimeter, a lightweight cotton shirt may ignite. One layer of flame retardant material typically provides protection up to 4 calories per square centimeter. 3 layers of flame retardant material typically provides protection up to 25 calories per square centimeter. The NFPA 70E 2004 revision includes several new requirements related to arc flash and energized work. Excerpts outlining some of the requirements follow. Appropriate safety-related work practices shall be determined before any person approaches exposed live parts within the limited approach boundary by using both shock hazard analysis and flash hazard analysis. A flash hazard analysis shall be done in order to protect personnel from the possibility of being injured by an arc flash. The analysis shall determine the flash protection boundary and the personal protective equipment that people within the flash protection boundary shall use. If live parts are not placed in an electrically safe work condition, work to be performed shall be considered energized electrical work and shall be performed by written permit only. The incident energy exposure level shall be based on the working distance of the employee's face and chest areas from a prospective arc source for the specific task to be performed. NFPA 70E Annex D outlines 2 methods for calculating the incident energy and flash protection boundary. One method follows equations originally published in the NFPA 70E and calculates values using 100% and 38% of the bolted fault current. The other method uses the IEEE 1584 empirical equations. Most engineers follow the IEEE 1584 method because the empirical equations provide a more accurate estimate of the arcing fault current. More test data and variables were used to develop the 1584 incident energy equations, and the IEEE 1584 equations are valid over a wider range of voltages and fault currents. The general steps required to perform an arc flash evaluation include determining the system modes of operation and a confidence tolerance of your system model, calculating a minimum and maximum bolted fault current at each equipment bus, estimating the minimum and maximum arcing fault current at each equipment bus, determining the arcing fault current seen by each protected device, determining the trip time of each protected device based on the minimum and maximum arcing fault current it sees, calculating the largest incident energy at the specified working distance, including appropriate arc fault tolerance, calculating the arc flash boundary, determining the required PPE level, and finally documenting the results and generating labels to be placed on the equipment. The bolted fault current should be as accurate as possible. While assuming an infinite source is conservative for sizing equipment, it is generally not conservative for arc flash calculations. When accurate data is not available, it is prudent to apply a minimum and maximum tolerance for the utility fault contribution and component impedance values when calculating the bolted fault currents. The IEEE 1584 standard provides an empirical equation to estimate the arcing fault current. The calculated arcing fault current varies with voltage, bolted fault current, gap between the conductors, and whether the arc occurs in open air or in a box. The trip time is determined based on the arcing fault current that flows through the protected device when the arcing fault occurs. Note that due to parallel contributions and voltage transformations, the fault current through the protected device may not equal the total arcing fault current at the equipment bus. When tolerances are used, the trip time must be determined for the minimum arcing fault and the maximum arcing fault. Additional environmental variables are needed to calculate the incident energy, including working distance, whether the equipment is grounded or ungrounded, and the equipment type with related bus gap. The incident energy is calculated in two steps, including a calculation normalized to a 0.2-second arc at a working distance of 610 millimeters, followed by an adjustment to the actual trip time and working distance. The first calculation includes variables for open air versus in a box, grounded versus ungrounded equipment, the arcing fault current, and the gap between the bus bar conductors. The second equation includes variables for voltage, the normalized incident energy, arc duration, working distance, and the type of equipment. The flash boundary is essentially a reverse calculation to determine the distance where the incident energy is equal to 1.2 calories per square centimeter. PPE stands for Personal Protective Equipment, such as fire retardant shirts and pants, shown on the left, and flash suits and hoods, shown on the right. The PPE should be based on the highest expected incident energy from the calculations. The NFPA 70E 2004 standard provides 5 arc rating levels of PPE. Class 0 for incident energy up to 1.2 calories per square centimeter. Class 1 for incident energy up to 4 calories per square centimeter. Class 2 for incident energy up to 8 calories per square centimeter. Class 3 for incident energy up to 25 calories per square centimeter. And Class 4 for incident energy up to 40 calories per square centimeter. Once the incident energy, flash boundary, and required PPE is determined, labels should be generated and displayed on each piece of equipment. Multiple labels may be placed on a single piece of equipment depending on the access point and proximity to the arc source for a given activity. However, often a single label for the largest incident energy is used. We will now review some important issues and concepts that affect arc flash calculations. A small reduction in available fault current can result in a large increase in incident energy due to a longer trip time. The IEEE 1584 standard compares the trip time and incident energy for 85% and 100% of the calculated arcing fault current to account for variations in test data. It is also prudent to apply a tolerance to the fault calculations themselves to account for inaccuracies in the system model. While evaluating the minimum and maximum fault current won't guarantee the absolute maximum incident energy, the large jump in incident energy that can occur when the fault current drops below the instantaneous region of the protective device will be accounted for. Current limiting protective devices can reduce incident energy by clearing the fault more quickly and by reducing the let-through fault current. These current limiting effects are typically only applicable at high fault currents. Since the arcing fault current is often substantially less than the bolted fault, the current limiting effects must be evaluated carefully. When the fault current is in the current limiting range, it is usually sufficient to use the faster trip times associated with current limiting devices without making adjustment for the reduced let-through current. Arcing faults that clear in 1/2 cycle as required in current limiting devices will typically not result in high incident energy. As an example, using the 0.01 total clear time from the fuse curve shown and an 18-inch working distance, even 200,000 amps of let-through current results in incident energy of only 2.4 calories per square centimeter. Reducing the fault current to 100,000 amps only decreases the incident energy to 2.3 calories per square centimeter. Reducing the fault current to 50,000 amps results in incident energy of 1.2 calories per square centimeter. So even for 200,000 amps, clearing the fault in 0.01 seconds results in Class 1 clothing. The point here is that clearing the fault faster is more important than limiting the current. The real advantage of current limiting devices in terms of arc flash is that they clear the fault more quickly. Most arcing faults are fed from parallel sources. It is important to understand that the energy at the fault location will be based on the total fault current from all of the sources, while the time required to clear the fault will be based on the portion of the fault current that flows through the protective device. It is also important to understand that some fault sources, such as utility feeds, are constant, whereas other fault sources, such as induction motors, are transient and only contribute current for a few cycles. For the example shown here, the 30,000 amp utility fault contribution to the arcing fault is cleared by the protective device in 0.5 seconds. The 5,000 amp motor contribution decays to 0 during the first few cycles. To be conservative, let's assume that the motor contribution is constant and drops to 0 at 5 cycles. A bar chart of the energy profile is shown. For the first 5 cycles, the worker is exposed to current from the utility and the motor. For the next 0.42 seconds, the worker is exposed to current only from the utility, since the transient motor contribution is removed. Using the total fault current at the bus to calculate the trip time and the incident energy would produce erroneous results. It is important to consider both fixed and transient contributions and to determine the fault clearing time based only on the portion of the fault current that flows through the protective device. Traditionally, fault calculations have been used to provide a basis for conservative equipment selection. Utility contributions were often represented as an infinite source. For arc flash hazard analysis, it is important to estimate the available fault current as accurately as possible. As we have seen, this is because smaller fault currents often produce larger incident energy because the protective devices take longer to operate. It is also important to evaluate alternative operating modes that may result in lower fault currents. Protective device coordination has traditionally been used to protect equipment and to provide reliable system operation. Arc flash protection requires a new safety focus for coordination studies, often needing faster trip times at the lower arcing fault currents. Alternative protection schemes such as differential, zone interlocking, and arc sensing trip units may also gain popularity. The faster you can clear the arcing fault, the less energy will be released. However, faster trip times often cause less power system reliability through reduced selectivity and an increased chance of nuisance tripping. However, life safety concerns always take precedence. The challenge of faster trip times is further complicated by the lower arcing fault currents, especially when a tolerance is used to estimate a range of possible arcing faults. The yellow bar represents the range of arcing fault currents. With the existing protective device settings, the high tolerance arcing fault would be cleared by the instantaneous function of the breaker. However, the low arcing fault current would be cleared by the long time delay function of the breaker at nearly 10 seconds. Note that for long trip times, the incident energy will be extremely high, even for low arcing fault currents. For these cases, you may want to evaluate a maximum arc duration, such as 2 seconds. If the energy released over the first 2 seconds is relatively small and proper PPE is worn, in most cases the worker will have an opportunity to move away from the arc. Use of a maximum arc duration requires engineering judgment and must be evaluated on a case-by-case basis. Hand calculations and spreadsheets can be used to calculate incident energy and flash boundary values. However, the process is tedious. Simplified calculators and full system modeling software can further automate the process by calculating fault currents, applying tolerances, determining trip times, and generating labels and work permits automatically. SKM Systems Analysis offers both a simplified calculator called ArcCalc and a full system modeling software package called Power Tools for Windows to automate arc hazard analysis. Looking at the advantages and disadvantages of each calculation method, a spreadsheet is an inexpensive tool that can automate some of the arc flash calculations. However, you still need to manually determine a minimum and maximum fault current at each bus, manually determine how much of the total arcing fault current flows through the primary protective device, manually determine the trip time from manufacturer's trip curves, and manually document the results in report and label formats. Determining the trip time is the most time-consuming process and is prone to error when processed manually. The ArcCalc Calculator is unique in that it is designed specifically to automate arc flash calculations. The calculator applies tolerances to determine minimum and maximum arcing fault currents. Using a validated library of protective devices, the time required to clear the minimum and maximum arcing faults are automatically determined. The resulting incident energy is reported in one-line, custom label, and work permit formats. Both calculation methods described in the NFPA 70E standard may be used and compared. The only disadvantage of the ArcCalc calculator compared to a full network software program is that ArcCalc is based on a fixed power system layout. The fixed layout requires you to view your power system as small interconnected pieces. The fault current calculated at one point is then used as the input source to calculate the fault current for the next part of the system. Whereas for a network calculation program, once the model is built, calculations can be performed for every equipment location simultaneously. The advantages of a full network software solution, such as the SKM Power Tools Arc Flash software, is that the calculations are performed for the entire power system model simultaneously. The SKM Power Tools network software solution has similar advantages as the ArcCalc calculator, including automatic determination of bolted and arcing fault currents, automatic determination of protective device trip times, and automatic generation of reports, custom labels, and energized work permits. The SKM Power Tools network software solution also has the advantage of integrated protective device coordination drawings and a scenario manager to easily evaluate alternative designs and configurations. The disadvantage of the full network modeling solution is that it is more expensive than the simplified ArcCalc calculator, and it requires more time and expertise to develop an accurate system model. The following example will review the Arc Flash calculation process using a network power system model and the SKM Power Tools Arc Flash software. The first step is to build the power system model graphically by selecting and connecting the cables, transformers, power sources, protective devices, and equipment buses. The result is a one-line diagram similar to the one shown here. A design voltage is assigned to each voltage level in the power system model. The cable impedance can be specified by selecting a cable type from the library and by entering the cable size, length, and the number of conductors in parallel. For each transformer, enter the voltage ratio, size, connections, and impedance. Enter the available short circuit current for each utility source in the power system model. Enter the size and impedance values for each generator in the model. Enter the rated size and impedance for each motor, and select the type, size, and settings for each protective device in the power system. When the system model is complete, you can simply run the Arc Flash calculation option. The bolted fault current and arcing fault current is calculated at each equipment bus. Based on the arcing fault current through each branch, the trip time of each protective device is determined. From the arcing fault current and trip time, the incident energy, flash boundary, and required PPE is reported for each equipment bus. The results can be displayed and printed in a custom label format. All of the labels can be printed in a single operation. The labels can be printed to plain paper for lamination or can be printed to vinyl label stock using a thermal printer. The results can also be displayed in an energized work permit format. The Scenario Manager can be used to evaluate alternative operating scenarios. Each alternative operating scenario should be evaluated to determine the largest possible incident energy. The scenarios can also be used to evaluate the effect of proposed design changes. Next, we will contrast the Power Tools Arc Flash network modeling software with a simplified ArcCalc Calculator. The ArcCalc Calculator has a single screen interface that displays a simple power system one-line, input data, and Arc Flash results in label form. The ArcCalc Calculator is ideal for evaluating small systems and for performing quick calculations at a specific location when minimal system data is known. The ArcCalc Calculator is similar to a full network modeling software program, but looks at one part of the system at a time. You essentially divide the power system into smaller pieces. For this example, we will use the portion of the system in the highlighted area labeled Network 3. Note that calculations for Network 1 and Network 2 can be used to provide the fault current source into Network 3. This diagram shows an expanded view of Network 3, which consists of a primary transformer and cable feeding the fault location. While the full network model relies on accurate data for the entire system, the ArcCalc Calculator allows you to apply generous tolerances to account for inaccuracies in the system data. To determine the arcing fault current at the equipment bus, the voltage and available fault current at the primary side of the transformer is entered. A minimum and maximum short circuit contribution is entered to account for variation. The transformer size is entered, which provides a default impedance. If you have the actual transformer impedance, enter it and remove the tolerance, otherwise use the typical data and impedance tolerance. Enter the cable type, size, length, and number of conductors per phase. A typical impedance is provided based on the conductor size and type. Use a generous impedance tolerance to account for variations in cable length, operating temperatures, and typical impedance values. For the main protective device, the library button is used to select a specific device. In this case, an ABB KDON breaker. The protection device for this example is on the load side of the transformer, although it can be moved to the primary side. The actual protective device size and settings should be selected. The settings will determine how fast the arcing fault current is cleared. Select the type of equipment at the fault bus. This will provide typical bus gap and working distance values. A description of the equipment can also be entered. If parallel motor contributions exist, enter the size, type, and number of motors. You can also indicate the time period to include the motor contribution in the incident energy calculations. The default value is 5 cycles. When the entry is complete, press the Calculate button. The calculator determines the minimum and maximum arcing fault current at the equipment bus, the required trip time for the primary protection, and the resulting incident energy, PPE class, and flash boundary using the IEEE 1584 and NFPA 70E calculation methods. The largest incident energy and flash boundary after evaluating both the minimum and maximum arcing fault conditions is displayed. The results are displayed in a custom label format. The results can also be displayed in an energized work permit format, which can be modified for a specific function. The input data and study results can be stored and printed in a simple one-line diagram format. The minimum and maximum arcing fault values, associated protective device trip times, and resulting incident energy and flash boundary values are reported. In summary, the amount of energy released during an arcing fault depends upon the voltage, the current, and the arc duration. The arc duration depends on arcing fault current magnitude and the protective device settings. The National Electrical Code requires arc flash warning labels. OSHA, through NFPA 70E, requires arc flash calculations and energized work permits. The ArcCalc Calculator is a perfect tool for quickly estimating the incident energy and flash boundary at any point in a power system. It is especially useful when insufficient time or information is available to perform a full system study. To contact SKM Systems Analysis about the ArcCalc Calculator or the Power Tools Network Arc Flash Calculations, call us at 1-800-232-6789. Please share this educational DVD with anyone you think will benefit from a better understanding of arc flash calculations.